Hello everyone. In this video we are going to discuss the force experienced by two parallel current carrying conductors which are kept at a certain distance and which are infinitely long. Actually, in the previous videos we have already discussed that when a current carrying conductor, straight conductor, is placed in a magnetic field, it experiences force. Now, instead of having a separate magnetic field, we are now having two parallel current carrying conductors. One current carrying conductor is placed in the magnetic field of the other. So both of them will experience force. So that force we are going to calculate. So let us see how it is done. Let me show you the diagram here. Here you can see there are two conductors we have considered. Conductor 1 carrying current I1 and conductor 2 which is carrying current I2. Now these two conductors which are carrying current I1 and I2, you can see here both the conductors are in the magnetic field produced by the other conductor. Let me give an example here. Suppose you consider the first conductor which carries current I1. Now when we consider this conductor, suppose you take your right hand in such a way that you hold the conductor 1 which is carrying current I1, then the curved fingers, you can see it goes in the inward direction, inward to the plane of the paper. We are considering the two conductors to be in the plane of the paper, so magnetic field is directed inward to the plane of the paper for the conductor which carries current I2. B1 is the magnetic field because of the current carrying conductor 1 which is carrying current I1, and that's why we can say that the I2 is affected by the magnetic field B1. That is, I2 current is flowing through the conductor in which the magnetic field is B1 which is in the inward direction. They make an angle of 90 degrees, so we can use the Fleming's left hand rule. This Fleming's left hand rule we can use to find the direction of force acting on it, which is given by F2 here. You can see the forefinger represents the direction of magnetic field. The middle finger, that is the central finger, represents the direction of current, and the direction of force will be given, F2 will be given by the thumb. So you can see that the direction of force on the second conductor which is carrying current I2 is given by F2. In the same way, for the current I2, there will be magnetic field. If we consider our right hand thumb, then we will find the direction of magnetic field B2 which is shown here, which acts on the conductor 1 in the outward direction. So accordingly, again using the Fleming's left hand rule, we can find the direction of the force F1 which is towards the conductor 2. So we can see that F1 and F2 both are in the opposite direction and the two conductors will attract each other. That is, when the two current carrying conductors carries current in the same direction, then they attract each other by the force which is given by F1 and F2. Now, we are going to derive the formula for the force. We know that for a conductor which carries current, the value of force on the conductor placed in a magnetic field is given by BIL sin theta. Now we are going to use that same formula and we are going to find the value of force. So first of all, we are going to find the value of F2, and the value of F2 is the force which is acting on the conductor 2. So the magnetic field B1 which acts on the conductor 2 due to the conductor 1 will be given by mu naught by 4 pi 2 I1 by R. Or we can write mu naught by 2 pi, if we cancel out 2 and 4, then it is mu naught by 2 pi I1 by R. And the distance of the point is R from the conductor 1. So the magnetic field is given by B1. Now The next thing which we are considering here is the value of the force. The formula is BIL sine theta. The value of B is B1. The current which is passing through the conductor 2 is I2. B1 is the magnetic field acting on the conductor 2. And let's say L be the length of the conductor. And sine of the angle between the current element and the magnetic field is 90 degrees. So sine 90 degree, which is 1. So we have a relation here. We can write here I2L into the value of B1 we are writing mu naught by 2 pi I1 by R. And after solving it, we have the final relation mu naught by 2 pi I1 I2 by R into L. Or we can also write mu naught by 4 pi 2 I1 I2 by R into L, where L is the length of the conductor. Now let us consider that we have to find the force for the unit length only. So force on the unit length of the conductor will be F2 divided by L, which is L will cancel out here in this equation, so it becomes mu naught by 2 pi I1 I2 upon R. So I hope that this is very clear to you. This is the value of the force acting on the unit length of the conductor. Next. Now using the Fleming's left-hand rule, the direction of these two forces, which I have already explained, F1 and F2, can be calculated. We have actually calculated the value of F2, that is the force acting on the second conductor. The similar value will be obtained for the force F1 which acts on the first conductor, and they will be exactly the same in magnitude, but their directions are opposite. So we'll write it as F1 is equal to minus F2, showing that their directions are opposite. Now let us consider another condition in which the direction of current are opposite. Two parallel straight conductors having current in the opposite direction. Then again we can see that for I1, that is the current in the conductor 1, the magnetic field here in the conductor 2 will be given by B1. And B1, using the right hand thumb rule, it will be in the inward direction. So if it is in the inward direction, using the Fleming's left hand rule, the direction of force can be calculated, and this time it is in a direction away from the second conductor. Similarly, for the conductor 2, I2 is the current, so the magnetic field B2 will be in the inward direction which acts on the conductor 1, and therefore the force using the Fleming's left hand rule is given by the direction as shown here. So here also F1 and F2 are opposite to each other and they will have the same value. But the difference here is these two conductors now will be repelling each other instead of attracting each other. When the two conductors, the current were in the same direction, then they were attracting each other. Here when the current is in the opposite direction, then they are repelling each other. So I hope this is very clear to you. So again the same formula stands. F1 and F2 are equal in magnitude but opposite in direction. So what we can write here is parallel current attracts and anti-parallel current repels. So I hope this is very clear to you. Now on the basis of the formula that we have obtained for the force on the unit length, that is mu naught by 2 pi I1 I2 by R, on the basis of that formula we are actually going to define the unit of ampere, unit of current, that is ampere. We are going to define 1 ampere. So two parallel current carrying conductors I1 and I2 we have taken here. Now you can see here in this condition which we are considering, let us consider I1 and I2 to be 1 ampere. That is both the current I1 and I2 is 1 ampere and the distance between the two conductors is 1 meter. Then the force on the unit length will be given by, according to the formula, if we put the values mu naught by 4 pi I1 I2 by R, all the I1 I2 and R have unit magnitude, so we have mu naught by 2 pi, which is 2 into 10 raised to the power minus 7 Newton per meter, because it is the force per unit length. So what we can say is the current through the conductors will be 1 ampere when they are the conductors are separated by a distance of 1 meter and they experience a force of 2 into 10 raised to the power minus 7 Newton per meter of their length. Let us discuss the statement here. 1 ampere is that value of steady current which on flowing in each of the two parallel infinitely long conductors of negligible cross section placed in vacuum at a distance of 1 meter from each other produces between them a force of 2 into 10 raised to the power minus 7 Newton per meter of their length. I hope this is very clear to you. Two parallel conductors carrying current in each of them to be 1 ampere. It will be 1 ampere when the distance between them is 1 meter, such that they experience a force of 2 into 10 raised to the power minus 7 Newton per meter per unit of their length. So I hope this is very clear to you. Any doubt, you can post me the doubts. Thank you.